right, hey, beautiful class. Let's get this last section in chapter 8 knocked out. Okay, so we've been talking about SN2 reactions, then we talked about SN1 reactions, we've talked about E2 and E1. We kind of went back into detail about E1 and SN1 and talked about how both things can happen given certain circumstances. And today we're going to go back and kind of revisit E2, and then we'll go back to SN2 and see when which situation occurs. Then we'll put it all together and make sure we're comfortable with it. So let's start by remembering what E2 is. So if you have some kind of, I don't know, thing. I don't know, something like this, and you react it with a strong base. Now, because this is a strong base, we kind of already have an idea what might happen. Now, you might want to say that we're going to see SN2 or E2, but keep in mind this thing right here is tertiary. So that's going to play a role later. So this bromide is tertiary, so if an alcohol is tertiary, it actually wants to go via SN1, right? But we have a strong base, so that pretty much leaves only E2 as an option. So in this situation, don't forget that what a base does is it'll grab a hydrogen. This would be called our alpha carbon right here. And now we could technically call this one our beta, but we want to choose the more substituted one as our beta. In fact, they're all the same, CH3, CH3, and CH3, so it really doesn't matter. You can call this one beta 1, beta 1, and beta 1. You choose whichever beta you want. And you're going to form a bond between the two betas. So first, in order to do that, the strong base takes off a hydrogen, the bond from the hydrogen comes down here, and that kicks our bromide off. And so you'll have a CH3, a CH3, and now you'll have a double bond going over here. So if I were to draw this better with like this, with our sticks, we originally had something like look like that. Oops, I can pull this up. I'm sorry, guys. Can't even see what I'm doing. So this interprets to this thing right here. And so we could form that double bond on any one of those. All right. We would also have an HOH, in other words, water. And we would also have a bromide ion. Okay. So again, E2 happens. It's usually it's always one fell swoop. The base will grab a hydrogen. The bond from the hydrogen will come down, and it wants to land between the two most substituted carbons. So yeah, all right, so let's keep going. Where and which kind of reaction is going to occur will depend, when you have chiral centers, on where the hydrogen in the alkyl halide is, so where the actual halogen is on these things. So in this case, they're on the same side, and in this case, they're on two opposite sides. Now, if the base comes in to grab them on the same side, which is represented right here, we call that syn paraplanar. So in a syn paraplanar situation, you can see that the base is going to get awfully close to this one right here, right? This thing that's up. And these are kind of almost like a staggered conformation, right? And so when you're in a syn paraplanar situation, the base is often too big to grab that hydrogen. So this actually won't happen. It doesn't want to happen. However, if the hydrogen is far away from the bulky complex up here, in other words, the X, or our halogen, I should put an X there just so we know what we're talking about, it will actually grab the hydrogen and then the bond can form. And so this is a situation it likes. Okay, so of these two things, it prefers the anti. Put the heart there too, because this is easier to see, I think, than that. Okay, so it says, given That Me2 reaction proceeds with anti-paraplanar stereochemistry, as we now know. Draw the products of each elimination. And the alkyl halides in A and B are diastereomers of each other. And then how the products relate, recall, blah, 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 blah. Okay, cool. So C6H5, this would just be a benzene ring and a benzene ring here and here. Okay, so let's talk through this real quick. First of all, they're in the anti-planar situation because we have an H here and a bromide here on either side. Okay, so that's a good situation. That's when it wants to react. This, again, is equal to a benzene ring, and this is equal to a benzene ring. However you want to draw it is cool with me. But we know that this base is going to grab a hydrogen. Oop. We know that that bond's going to come down here, and it's going to kick the bromide off. The question is, what's going to happen to these benzene rings? So if you look at them, right now you have one coming toward you on the wedge, and one going into the plane on the dash. In other words, right now, technically, even though we could just switch it around, right? If you froze this in time, this would be a trans formation, right? And because of that, what you will get is a transformation. Transformation, but I mean trans space formation. Okay, so there's a C double bond C right here. On that C double bond C, I had a methyl group and this benzene ring. Like this, okay? And then on this carbon, I had the other methyl, or the other benzene. Okay, and I had the bromine there originally, now it's just a hydrogen. Okay, so we would get the trans conformation. Now this is an actual trans conformation because remember, a double bond can't twist around each other. So here we could have just twisted it around and gotten something similar that looked like this. But in this case, if I give you a problem like this, ask you to find me the product, because this started off where the bulky groups were on either end, you're going to end up where the bulky groups are trans conformation. Okay, so let's work on this one. Here we have the bulky groups are both pointed into the plane. In other words, they're technically, I should put this in quotes, they're technically kind of cis-like. Okay, and therefore when you do this reaction, you'll get a cis-like conformation. So here we'll have the benzene ring up here. We'll also have the benzene ring up here. And then we can't forget about that CH3 and the hydrogen. So this would be a cis. So the original stereochemistry does matter in which product you end up getting. Stereochemistry continues to matter on cyclohexane substituted things. So for example, if you have a chair conformation like this, remember that, let's say we started with a Cl here. If it underwent a transformation, the equilibrium would go this way. We'll talk about why, even though we might already know. There's my dog. He says hi. That's corduroy. It's cool, dude. You end up with the chlorine down right here. Remember that this is called axial, and this is called equatorial. Also remember, we're drawing a bigger arrow this way because this is more stable. Okay, so herein lies the problem. If you have something that's really stable, why would it want to change? Like if you reacted this with, say, a base in an E2 reaction, why would the base want to grab a hydrogen if this thing's already really low energy? And the fact is, it doesn't. It actually won't react. So this one won't react. It's too stable. They're too happy. This one will. All right, it's high energy. It doesn't want to remain this way. It's happy to react. Let's put through a few. Oh, hey, look. I just brought you to the next page. Okay. So true to form, this is equatorial, so therefore this one will not react, but this axial conformation where the Cl is down there will. And what's going to happen is the base will grab a hydrogen, whichever is going to be the most substituted hydrogen will be your beta 1, and that's going to result in a chair conformation, and then of course we could draw it like a regular cyclohexane. Let's do an example. So let's say you have this thing. So it's equatorial, the heavy things axial, and this one's equatorial, but the heavy thing's axial. So this is good. So this will react. So it will react because the chlorine is axial. It's a high energy conformation. Okay, so let's talk about it. If we draw the chair conformation here, a base is going to come in and it's going to grab something. Now, I know they already labeled these. I really kind of dislike that. The reason I dislike that is because in class we talked about labeling the most substituted carbon next to the carbon that has the halogen on it as beta 1, because that means that that's where your double bond is going to go. Okay, so if that's the case, this one right here is the most substituted. Let's call that beta 1. And you could call like the other hydrogen over here beta 2. Okay. So again, it's always going to want to choose the more substituted one as the major product. So our beta 1, the CH3 doesn't change. It's going to be right there. So we're just going to form between our alpha and our beta 1, which will be right there. That will be our double bond. This will be our major product. Now you could also get a minor product, which would be between the alpha and the beta 2. Which I didn't leave a lot of space for, but it would be right there. You could redraw that as a cyclohexane. And that. So these two are equivalent. Okay, so hopefully that helps a little bit. All right, now let's kind of throw it together and see if we can think through this problem here. It says draw the major E2 elimination product formed from this reaction. Okay, so we know that in an E2 reaction, we want to pull off a hydrogen that's the most substituted, right? So let's draw that hydrogen real quick. Because we have stereochemistry, we actually have to worry about the hydrogen now. Remember, if they're periplanar versus synplanar, is going to make, or anti-periplanar versus syn-periplanar is going to make a big difference, right? So we want it to be anti-periplanar, meaning on two different sides. But if you look here, this hydrogen is on a wedge, and this is on a wedge. So if we call this thing alpha, we want to originally call this our beta 1 because it's the most substituted carbon, right? But it's impossible because this one is on the same side. They're both pointing into the plane. And these are, in other words, these would result in a cis situation, and we can't have that. It won't do that, okay? So any syn-periplanar situation won't occur. So the only hydrogen it can take, that was going to be our beta 1, our only hydrogen it can take is right here. And so the product that we'll get will be where we form between here and here, like that. And then everything else remains the same. We didn't touch this thing up here. And we didn't touch this ethyl group over here either. So anytime you have stereochemistry, take a good hard look at it and make sure that the hydrogen is on the opposite side of the halide. Otherwise it won't react. Ooh, this is fun stuff. I think this is intuitive. You guys will knock this out. Okay. Dihalides. How cool is this? So in a situation like this, where you have two halides, In other words, it's called a dihalide. You're going to get a pi bond because you'll react it with 2. And remember how we talked about reacting with excess or 2 equivalents, meaning 2 times what you need for this, for a single reaction? Then you're going to get a triple bond instead of a double bond. So normally you get a double bond, but here you're going to get a triple bond, which is really, really, really cool. I'm going to, let's learn a little bit of vocabulary. When they're on the same side, or on the same carbon like this is called a germinal dihalide. And when they're on separate carbons like this, it's called a vicinal dihalide. Okay, so you might be maybe a little frustrated with the fact that this bond happened here, because if you were to do, well, actually, that's the only way that it would work. But let's say the chlorines were here and here. You might want it to be over here and have a double bond there and another double bond there. But that couldn't have happened because we have the 3 bonds here. So make sure that you never end up with 5 carbon bonds, which is kind of easy to do when you're adding 2 new bonds. So be careful there. Okay, what else we got? Also, it says minus 2HCl. That won't be like given to you on an exam. You won't know what it loses. You're just gonna have to know. Okay, you're gonna have to know that that's a strong base, that that's a strong base. Hey, look, dimethyl sulfoxide, that's a polar A product solvent. Okay, let's keep going. Let's see if this makes sense. So here we have a vicinal dihalide. We're going to go ahead and react it with a strong base. You could say excess base or any kind of base. But in your E2 reaction, the result will be that you get something like this, and then the triple bond will form there. And then we still have this ethyl group after it, like that. If you're like me, you want to draw it like this, where you go, you like to follow the same pattern so you don't miss anything. And then you do a triple bond like that. Technically, triple bonds are linear, but I think I told you at the beginning of the semester, I always like to draw it like this. So I'm cool if you guys do that. But as long as you have the bonds correct, I'll know what you mean. Okay, and then we get over here. There's only pretty much one place we can put the triple bond, right? Oh, and here was one of those situations like what keeps you from putting the triple bond there? It has to be between the 2 vicinal halogens. Okay, so here we have another situation where I would want to go like this, personally. Or not like that, I would want to go like that, and then draw my triple bond there. Or you could be fancy and do something like this, which is actually correct. Fancy is the correct way to do it. All right, hope that makes sense. Moving on. Okay, so let's put all this together. We've talked about SN1, SN2, E1, E2. This isn't a review, so I'm not going to go through all of them and all the individual conditions, but we are going to do several reactions. And just kidding, I am going to go through them all and all the conditions. Whatever, man, I'm going to do it. Okay, let's do it. So we have SN1. I'm going to put SN2 first because I like SN2 first. E1 and E2, kind of the order that we learned them. That's not true. We learned E2 and then E1, like this. Let's do that, okay? I already did a horrible job because I was going to make a table, but I'm going to put my headings over here, guys. So let's say, what do they like? Like tertiary, secondary, the substitution that they like. Remember, SN2 only does primary and secondary. SN1 only does secondary, tertiary. E1 and E2 both prefer secondary and tertiary. Okay, they can do primary, but they prefer not to. Okay, so primary is like So for example, if you're ever got like an SN2 reaction and you're not sure if an E2 will occur, but it's on a primary, your major product will be an SN2, not an E2. Okay, let's go over solvents, or actually base, nuke strength. So R2s prefer strong. They love that negative sign. But for an SN2, it doesn't want bulky. So it's cool with strong, but not bulky. So if you have a really strong base that's really also big, and conditions that would occur for both SN2 and E2, it will only go via E2. Okay. For our SN1, it prefers weak. For our E2, strong and bulky is cool. And for our E1, weak. Okay, last but not least, I don't know what I'm doing, it's a pretty poor table here. You can tell I'm just pulling this out. Solvents. So I posted a list of solvents online. I really suggest you guys memorize them. There's not too many, but having those in your head, like for example, if I say DMF, do you know what it is? Or DMSO or THF? Like you should know these solvents because they're going to show up in your exam. So SN2 prefers a protic, as does E2. But SN1 is protic, as is E1. So these prefer the hydrogen bonded solvents. Okay, so with that being said, let's take this information and go do these. Okay, so draw products of the following reaction. Here we have got a bromine. The very first thing that I see is that it's secondary. So I'm like, oh crap, it's secondary. That doesn't eliminate anything, right? But it's got a strong base. Okay. This ended up being just a result of the product, not necessarily the solvent. I kind of really hate this because you look at it and you're like, oh, it's a polar product. Let's just do this. Let's pretend that doesn't exist. Cool, cool. I wouldn't have it on your exam. Okay, so let's go ahead and go through it. We have a strong base and a secondary bromide. So you want it to occur. You're like, okay, this could be SN2 or E2. There's no conditions that keep it from being either, right? So let's go ahead and do it. Via SN2, our product would be a straight up substitution. Cool. There's no stereochemistry, but if there were, it would be the inverted, whatever this was. And then our E2. They're all equally substituted. Oh, sorry, I just realized this is a pentagon. There we go. A pentane. With our E2, we'd end up just getting something like that. You could have put that double bond anywhere. So, all right. Let's do the next one. So this is fun. Here we have, this is a tertiary substituted. So this could occur via SN1 or E1. It's a weak base, so it could have even been E2 with the tertiary, but because it's a weak base, that tells you both of those are valid responses. So let's do our SN1 reaction. And our SN1, we get a straight up substitution here with the Br. And we'd get an OH, like that. Okay, we would also end up with like an H3O plus, if you remember that water comes back and grabs an extra hydrogen. And then with our E1, we're gonna end up with, once that leaving group leaves, which would be the first step of both of these, leaving group leaves, leaving the positive charge, and the SN1, the water comes in, And the E1, once it leaves and you have a positive charge, the base comes in and grabs a hydrogen. Which hydrogen is it going to grab? Well, if it grabbed it from here, and we had this, even though it's way substituted, you'd end up with 1, 2, 3, 4, 5 bonds on a carbon. You can't do it right there. So it has to grab it from either one of these sides. It doesn't matter which side you choose. I'm going to choose that one. Yay. Okay, as much as I want to stop there, this is the way, there's more class. So, there's more. Let's do lots of practice, okay? Let's see if I can find some more. Probably need it. Drawing with a marker is always kind of hard. Okay. So, in this first reaction, we have what appears to be a strong base. Right? It's got a negative charge, but I hope you agree that's a bulky base. That's the tert butoxide. So you got an O negative to a carbon to CH3 like that. Dude's big. Okay, so something to think about. All right. The other thing to think about is that this is primary. Okay, so you want it to, when you think primary, you're immediately thinking E2 and SN2, right? Possibly E2, because we know that it doesn't really want primary. But this is so bulky that it's going to override, and it's going to want to proceed via E2. So anytime you have a really strong bulky base and it's primary, it's going to go via E2. And we'll end up with something like that. Okay, it's like a B. Okay, so this is primary. This is a strong, less bulky base. So it's really happy. So if we go like over here, we're like, okay, we got a strong, low bulky base, primary. Strong, bulky is fine, primary. So it could go SN1 or SN2. Remember I said though, if it has a choice between going SN2 or E2, sorry, I just realized I said the wrong thing. It's gonna go SN2 or E2. But E2, anytime it has a choice, it prefers not to go primary. And because of that, you will get the SN2 reaction here. This. And we'll just attach it to an O, CH2, CH3. I still have that methyl group down there. Cool. So again, strong base, bulky, E2. Strong base, not bulky, but primary, SN2. So hopefully that gives you an idea of how it wants to proceed. The next one's kind of fun. We can automatically see it. Yay, we got 2 equivalents. Those are gonna be super fast. You know you can't, if you put the double bond here, actually you could put the double bond there. Interesting. I'm going to have to look into this one. This one doesn't like me. You're gonna end up with a triple bond there and there. Oh, because it's a triple bond, that's why. You couldn't put a triple bond in the other place. All right, so we got a triple bond, boom, 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 and that would be your result. All right, I'm going to go give my dog a carrot because he won't stop barking and it's distracting me. There, dog, have a carrot. What a good dog. My poor dogs. They're on a diet, but I fed them carrots until they now just think that they're treats. Okay, next one. DBU. I'm trying to think of how you're going to remember this, but this is a big, this is a huge base. Strong. It's like this nitrogen containing thing. It has like actually like almost an octane in it. But it's big. So let's keep that in mind. Here it's primary. So it can go via either E2 or SN2, right? But it's a big, strong base. So just like up here, we had a primary with a big bulky base. And so we only went via E2. The exact same situation will happen here. We have a strong base, so it's only going to go via E2. This is our alpha, right? Our beta can only be here, so we'll end up with that. Okay, E. What do we got? We have a secondary there, so that leaves a lot of options. It could be SN1, SN2, E1, E2, but big, bulky base. It's also strong. Any option, big, strong base. That when it's a big, strong base, that immediately limits all the ones, the E1 and the SN1, right? And just like in A and D, with a big, strong base, we know it's got to go only via E2. If it goes via E2, we'll end up with this as our major product. Perfect. 1, 2, 3. I'm seeing if there's a more substituted one I should have done. Nope, I'm going with it. I think I wrote the wrong answer, but I like this one. Okay, let's keep going. I'm sure you will let me know if I screwed up in class. But as far as I can tell, this is my alpha, this is my beta 1. It's the most substituted, so it makes sense that it would drop between there and there. Okay, let's keep going. Here we have, notice this is a weak base. About time we had something that was SN1 or E1. So that makes it SN1 or E1. This thing is tertiary. Oh, so that means it can go via either. Cool. So let's go ahead and knock it out. If we go via, I'm gonna move it up here. If we go via SN1, we're just gonna do that substitution. Okay, and we'll have it going up to O, CH2, CH3. And then our ethyl group like that. So that'd be our SN2, our SN1 reaction, and our E1 reaction. Looks to me like we might have two different products. If this is our alpha, our beta can either be here or here. Okay, so either way, really, we get the same substitution. And we'll end up with that and that. All right, when I count, I see 1, 2, 3. So this is tri-substituted. 1, 2, 3. This is tri-substituted. I think this one would be more of a major product because it's within a ring. But that would be arguable. They're both tri-substituted. Okay, let's move on. Ah, yay, we got this one. Oh, I can't wait to teach you guys this and be like, it's so easy. All right, so we got this thing and that thing. We know when we have two bromides, the only thing it's gonna do is that dihalogen elimination reaction, dihalide elimination reaction. So that's exactly what we're gonna get. This bromine's gonna go away, that bromine's gonna go away, and their bonds are gonna come here and here. So we'll get that. All right, moving on. All right, I see a tertiary thing with a weak base and nucleophile. I see no reason it couldn't go via SN1 and E1. So let's go ahead and do that. Let's do SN1. In an SN1 reaction, we'll get OH here. And then in the E1, I see two products. We can get a major and a minor. This is the alpha, right? And so we could either put our beta here or here. The more substituted is here, so our beta 1's there, and our beta 2 is going to go there. So for our two products, we'll get one that is like that, where it was between alpha and our beta 1, and our other product, which would be our minor product, would be like that, where it's after the beta 2. So this one is major. And again, I'm willing to bet that this is, because of these electron donating groups, the carbons around this thing, I'm really willing to bet that this is also our major product. Is that it? That's it, dudes. All right. I feel like we successfully learned E1, E2, SN1, SN2 reactions. I posted that solvent list. You're going to have to memorize it. And I will work on getting some kind of nucleophile or base list so we can kind of get used to using them and know what's considered quote unquote bulky and what's not. So, all right, I'll see y'all later. Have a good one.